Welcome. My name is Ata. I'm a PhD candidate with EPFL. This project is part of my collaboration with Sabancı University of Istanbul. Today I will be talking to you about the merge of wearable and flexible electronics with neuroscience. As you know, EEG is a non-invasive method to record microscopic voltage fluctuations resulting from ionic current activities between the neurons themselves. It is extensively used in neuroscience, mostly to diagnose epilepsy, and more recently in novel units to alert seizure episodes. To pick up these bipotentials, clinical EEG usually acquires free-gelled electrodes. However, for mobile applications and remote healthcare, these types of electrodes have limitations. Shortly, these drawbacks are due to the drying of the gel after a while of using, which this results to the degradation of the recording signal-to-noise ratio. Throughout the years, people have proposed gel-less electrodes with either contact-based or capacitive coupling-based sensing mechanisms. But compared to other variants of dry electrodes, electronic textiles appears to be the key technology in wearable non-invasive monitoring of biological indicators. E-Textile promises flexibility, permeability to air and moisture, and accessible integration to daily clothing. Flexibility is essential here to enable skin compatible devices by matching the body's natural contour, thus achieving to a better skin electrode coupling, whereas permeability to air and moisture will elevate the possibility of skin irritation. Also, intelligent clothing that is clothes enhanced with e-textiles can embrace a critical role in a more extensive wireless body area network by including the embedded, flexible, and stretchable antennas and wireless transmission modules in order to enable a continuous transfer of all sorts of physiological information, which are sensed by the fabric itself to a remote medical unit or to the cloud, which can be examined on the spot or later on by a professional staff. Meanwhile, fabrication techniques in textile electrodes play a critical role in expanding this all textile intelligent clothing paradigm. Textile electrodes can be attached to daily clothes and accessories thanks to in-stream fabrication manufacturing approaches such as knitting and embroidering, or the sensing side can be applied to finished textile directly using electroplating, physical vapor deposition, chemical polymerization methods, or printing or various printing methods such as screen printing and deep coating. Actually, not so long ago, we published a review paper discussing this subject in detail. Deep coating is a serious game changer over other fabrication methods. This is due to its low manufacturing costs and adaptability of this method to the existing commercial roll-to-roll textile fabrication processes. Other fabrication methods usually require special equipment or processes that hinders their mass production. Well, in this study, we prepared graphene textile following a previously introduced scalable three-step deep, dry, reduce process. This fabrication process starts with graphene oxide preparation, and then we immerse the plain textile in gold solution. After that, each of the coated layers was dried to achieve homogeneous graphene oxide coated textile. Later on, the thermal treatment and chemical reduction were carried out to create conformal electroconductive graphene structure. After the reduction, textile were washed by immersing it into the deionized water to remove any unbound chemical residues from the fiber surface, and only stable and well adhered reduced graphene oxide foams remain on the textile. As you can see, during the conversion of graphene oxide to reduced graphene oxide, there was a noticeable change in the textile color from brown to black. This is due to the removing, of course, oxygen containing groups. Later on, for prototyping, the prepared e-textile piece was cut into a desired dimension and fixed on a flexible sticky form where it sandwiched an ordinary sports headband and metallic snap fastener in order to establish electrical connection with the front-end circuitry. To acquire higher signal-to-noise ratio and ensure interference stability, we have also used elastic bands with Velcro straps and foam padding to provide pressure approximately in the range of few millimeters of mercury to form a stable high contact area on the skin surface. Our group already reported the successful acquisition of cardiac, muscular, and ocular biopotentials with this fabrication methodology. For EEG, we only used hairless locations on the skull in this study, since textile electrodes are well known to perform best in less hairy sites. Forehead EEG is the best fit here, where active electrodes are at FP1 and FP2, and the reference is at FPZ. We are delighted to use Mental Labs data acquisition unit in this study instead of our costume design system. Mental Labs offer a compact and portable device and targets mobile EEG applications. For checking the functionality of the fabricated textile electrodes in neural biopotential monitoring, we benchmarked the EEG recordings using our graphene textile electrodes and the gold standard wet silver chloride electrodes. In this trial, the participant was requested to close his eyes for 1 minute and then open and read a text that appeared in a display. The figure above illustrates the acquired EEG signals after signal conditioning, and the correlation coefficient between these two recordings was calculated to be 91% during the entire 2 minutes of experiment. And the alpha waves usually oscillates between 7 to 13 hertz in frontal cortex when the subject is resting, and disappears when the mind is active. The figure below illustrates the short time Fourier transform of the recorded signals, where alpha rhythms can be tracked between 8 to 11 hertz when the eyes are closed and disappeared subsequently after opening the eyes. This sharp alpha wave disappearance in transition between eye close open state certifies the successful acquisition of alpha waves and EEG signals from the forehead using graphene textiles. Being said that, I thank you for your attention. Please let me know if you have any questions.